Hi, this is a continuation from Allen High School. Forgot my beginning page there, but that's okay. This is copyright Allen High School 2011. And let's take a look at some of these, copyright, watch them as you will, seriously. Now, this gives you an indication of what we were looking at. Remember, the S was a sphere, the P was a dumbbell, the D was kind of the clover leaf, and F is very funky. Now, we also have a letter for L, so this is both S and 0, and P would be the number 1, and D is the number 2, and F's the number 3 for our value for L. Now, the S, P, D, and F came from spectroscopy. We've talked about that, the interaction of light, electromagnetic radiation with matter. We're actually going to be doing a lab on that soon. I really love it, our copper penny lab. And after that, this came from like sharp, principal, diffuse, and I've heard both fine and fundamental for F. We don't have to know those words, but I just wanted you to get an idea of where they came from. After F, they start to go by the alphabet. But at this point, we're talking about excited states. A G orbital does not naturally exist, at least in what we know right now, the elements that we know. This would have to be, if you had a G in our model, it would represent definitely an excited state. Any state where an electron is higher than what we're going to be predicting is an excited state, but definitely if you saw G. So the question becomes, how do you memorize this? One of my students came up with this. I really love her. She's so funny. Some people can have all the lights on and still be in the dark. He came up with the phrase, stupid people die first, and I purposely misspelled that. But it gives you the idea. Stupid people die first, SPDF. And that gives us our acronym for our L values. There's another way too, I'll tell you in class. Now, this shows what we call radial distribution functions. That's what I was trying to sketch out for you on the edge, going from the center out to the edge of those. And what we have with our orbitals, not every single one, but not this one here per se, but we end up with nodes. Remember I said I'd mention that in a little while? So there is a little bit of probability that an electron in the second energy level, in the S sub-level, would be close to the nucleus. There's a finite probability, but it's much more likely to be found further out. So the bigger the area, the greater the probability of finding the electron. You notice for the 1s, it's much closer in than it is for the 2s, which in turn is much further in for the 3s, and so on and so forth. But you notice there are spots where it approaches 0. The probability of finding the electron becomes 0. And those are called nodes. It's kind of like if you play any stringed instrument where you have a wave attached, the string is attached, you can get a standing wave and you form a node. It's very much like that. So at the nodes, the probability approaches 0. And as we look at this, the area under the curve, the electron density gives you the magnitude of the electron density. I think that was repetitive there. So the area under the curve gives you the magnitude of the electron density, or really the relative amount of time that the electron spends in that area, or a greater probability. It's not shown here, but what we're graphing on this y-axis is psi squared. Remember, that's going to be our final wave function squared, our probability region. So as these go higher, our probability of finding that electron increases. Now let's look at our next quantum number. This is our third. And after this, we really have what we need to define that region in space where there's a 90% probability of finding an electron with a given energy. And this is called the magnetic quantum number. Magnetic because it was discovered that when there's a magnetic field, the spectroscopists ended up seeing 3 lines when they anticipated 1. So in a magnetic field, they split. And what this gives us is an indication of our orientation of an orbital. And mathematically, that should be an L there. M sub L takes on all integers, including 0, from negative L to positive L. So let's get an indication of what that looks like graphically, and then we'll take a look at the pictures of that back on that winter orbital diagram. So we've got a table, and we'll have N, and we'll have L, and we'll have M sub L. And as we're going, I want to help you see some of the ways we represent these. I'm going to see if the green doesn't show up much better. Let's try the black and help you out here. So if N is equal to 1, the only thing L can be is 0, because it can only go up to N minus 1. Now, M sub L can take on values from minus L to plus L, which is 0. Right? Now, what we call that is the S, remember? In here, we're going to use a single line. There is only a single orientation of a sphere, one way to orient the sphere. And some people use boxes or circles. I tend to use just a single line to represent that M sub L is equal to 0. Now, if N is equal to 2, L can be 0. Again, that's our S, remember? I don't know if those look like oxygens to you, but we'll put a line through them in case they do. And again, M sub L can still only equal 0, which we'll depict in our model we're about to build with a line. Now, L can also be the number 1, because N minus 1 is 1. So I have two possibilities here. We call those the P. And M sub L can equal minus 1, 0, plus 1. And we're going to be using those lines above those to depict that. So we'll have a line to represent each of these. Now, we're at the orbital stage at this point. These lines represent that orbital that we were after, that region in space where we can find electrons. Now, let's move to 3 and see what we have for 3. Well, if N is 3, L can be 0, 1, or 2, which means we have the S, P, or D available. Do you notice that we don't have a 2D? Because to have 2D, that means N is equal to 2 and L is equal to 2. And L can't be that high. Its upper boundary is 1. And so 2D is not allowed. That's what we mean by allowable. So if it's an S or 0, the only thing M sub L can equal is 0. So again, we have that single line to depict that. If L is 1, we've got minus 1, 0, and plus 1. And we'll use 3 lines to depict those 3 orientations. Remember, that's what we're after there. If L is 2, we get to start at minus L, so we get to start at minus 2. We've got to go integer up 1 through 0, plus 1, plus 2. And this time we have 5 possibilities. 1, these aren't necessarily even, but it gives you the idea. 2, 3, 4, 5. I hope you see a pattern here. So we went 1, 3, 5, and I'm guessing that you can figure out if we went to the 4th level, we can have an F. And if we have 1, 3, 5, you're right in guessing that this would have 7 orbitals associated with it. And that's what we saw in the picture, and we're going to revisit that right now. Now, you're going to have to assign quantum numbers. You're going to have to tell me whether or not something's allowable. So again, if you saw 3F and you were asked if that was quote unquote allowed, we would have to say no, because N is 3, and if we have F, that means L is 3, and my upper boundary for L is 2 there. And really what it's like is the electron just can't move in that space with that given distance from the nucleus and still maximize attractions and minimize repulsions. Now let's go and apply this very quickly to our website that we have. Let's go back to, let's just start with our 2s. So if we had 2s here, we would have n is equal to 2, L is equal to 0, and there's only a single orientation. So m sub L is also equal to 0. So let's do m sub L is also equal to 0. One orientation. Now let's go to 4s. It doesn't matter what energy level we're at. An S, in a sense, an S is an S is an S. So if we have here 4s, n is 4, it's given by the number in front. If we have s, that means L is 0. If L is 0, the only thing m sub L can be is 0. And we have one orientation that we're ultimately going to represent with a line. So that would be a line there, a single line. Can't quite see it because I didn't use a very good color for you. All right, now let's take a look at the P. Let's go back to 2P. It's less complicated. A dumbbell has 3 orientation, X, Y, and Z. And I'm not going to make you distinguish between them. I just want you to know that there are 3 of these. So if we have 2P, that means n is equal to 2 because that's the number in front. If we have P, that tells us L is equal to 1. Right? We'll get into that. Remember, it's 0, 1, 2, 3, stupid people die first. You know, do a brain dump and get that down on your paper as quickly as you can. Now, if L is 1, that means that m sub L can be minus 1, 0, and plus 1. And we'll depict that with 3 lines because we can't draw those dumbbells all the time. And that's why the P has 3. Now, it doesn't matter if I'm at energy level 2. Now it's more complicated in terms of finding the electrons, but as we go up to, let's say, the 6p sublevel, we're talking about very big atoms at this point, larger elements, what we find is we have 3 again. So this is 6p, so n is equal to 6, L is equal to 1, minus 1, 0, plus 1. Now let me go to the D, and I hope you'll have it by then because this video is going to be too large to load up. Let's try the 5D, and let's assign quantum numbers to that. If it's 5D, n is equal to 5, L is equal to 2. So that means we'd have minus 2, minus 1, 0, plus 1, plus 2. Now, you're never going to have to link these by numbers. I'm just going left to right like we're reading. And so if I wanted to depict that in a model we're about to build, I'd put 5 lines for each of those m sub L's. A convention is it's minus 2, minus 1, 0, plus 1, plus 2 for those. All right. That's it for this video. We're going to continue this conversation in our next video.